Hello and welcome back to my physical science online lecture series. In today's introduction video, I wanted to talk about the topic of motion, and specifically the description of motion, which is called kinematics. And this is the topic of the second set of lectures in my physical science course, for those of you who are taking the online physical science course from me. The primary focus of this lecture is kinematics, which is the description of motion. And what that means is, suppose we have an object and it moves across a room. Well, there's many different ways that an object can move across a room. Maybe we mean it moves from one wall to the other wall. Well, did it take a straight line to get there? Did it move at a constant steady speed? Did it stop in the middle of the room and pause? You know, maybe it's like a cat that's pacing back and forth in the room. Did the cat stop in the middle of the room and stand for a little while and then double back, or did it just cross the room, or what happened? Maybe our object is a ball that's rolling down a ramp. So did it really move down the ramp at the same speed the whole time, or did it start getting faster as it went? Maybe it's going up a ramp, in which case it's probably getting slower as it goes. So kinematics is basically about describing the form that a motion takes. You could define it most easily for a simple motion using a set of several terms, specifically time, which sort of ties everything together, if you will. There is position, where is the object? And usually if you're talking about position, you're talking about where is the object with respect to some known location. So for example, I could give my position with respect to the wall that's sort of behind me. How far am I from the wall, and on which side of the wall am I? I could give my position even more specifically in terms of where two of the walls meet each other. So now I've given my position in 2 degrees. I could also give my position in 3 degrees by specifying a specific corner in the wall. Maybe I want to know where am I, or where is, for example, my webcam, what you're watching this video because of. Where is that located with respect to the point where 2 walls and the floor meet? So that's my position. And if I want to talk about moving, one of the easiest things to describe is change in location or change in position. When we talk about motion in physics, we usually mean what the old philosophers would have called local motion. So changes in location, not change in general. If you read like a Greek philosophers like Aristotle, for example, or even if you go into medieval times and you read, say, St. Thomas Aquinas, they will talk about motion, and what they really mean is change. So a acorn changes into a tree. It would be a type of motion from what a philosopher is basically talking about. They mean that something that is potential becomes actualized. When we talk about motion, though, we largely mean basically movement from one place or one location to another. So having defined position, the next thing that is of interest is change in position. And the change in position is called displacement. And to get displacement, you can take the the two locations, and again, depending on how you defined your locations, if I want to define everything with respect to the corner of my office in which the two walls meet the floor and where the door is located, then my position has to be given in 3 dimensions, or 2 dimensions maybe if you mean where are my feet placed on the floor. So if I want to know what's my change in position, I actually have to give 2 or 3, depending upon how many dimensions we want to talk about, changes. One is, how far away have I walked from the one wall of the room? How far away have I walked from the other wall of the room? How far above the floor am I? That largely isn't going to be changing, although I guess you could ask, how far above the floor is my head? And right now I'm sitting down. If I were to stand up, then my head position is changing with respect to the floor as well. So these changes in position are called displacements, and they need to specify all of the relevant changes that we're interested in. So change from with respect to the north wall, change with respect to the south wall, change with respect to the floor. That gives me 3 different things that I'm keeping track of. So one way to do that is to specify position as a vector and change in position as a vector. So that gives me how far away am I, but also which direction am I moving in. So that's displacement. And it's worth noting that an object can move without its initial and final positions having changed. By which I mean, you start a stopwatch, you go for 5 seconds, and you may end up in the same place that you were to begin with, but it doesn't mean you haven't moved somewhere in the room. One way of looking at this is that your total displacement on average for a given day is usually roughly 0. You wake up in your bed, in your bedroom, or in your hammock, or in your, whatever your sleeping arrangement is. You get out of that bed, you go to work, or you go to school, or you go to wherever you want to go for your day trip. You do the activity of the day, and then you return home and ultimately lie back down in bed. You have a total displacement of 0 there, and yet you've moved throughout the day. So we can track a difference between your displacement and the actual distance you've traveled. Some companies, as a health initiative, used to give their employees, and maybe still do give their employees, little devices that track how many steps their employees have taken for the day. And so they measure, okay, how much walking have you done today? You need to walk for at least a mile each day or whatever. I forget what the exact number was that my friends had to do when they worked for this company, but maybe 1 mile's worth of walking. Your whole displacement might be 0, but it doesn't mean that you failed to walk a mile on that day. So there's a difference between distance, which is only a scalar or a magnitude, and displacement, which has a direction as well as a distance. We can also talk about change in velocity per unit time. Change in position per unit time, which is called velocity. So velocity has a magnitude, which also happens to be the speed of the object, and it has a direction. So how fast is the object moving, and in which direction? And again, on average, if your total position change is 0, then your average velocity for the day is 0. That doesn't necessarily mean that your speed at any given moment is also 0. Nor does it mean that your velocity at any given moment is 0. So you can find an average velocity by dividing the total displacement by the amount of time it took to get that displacement. If you want an instantaneous velocity, you do the same thing, except for that you take very, very short amounts of time. Strictly speaking, you do it as the increment of time approaches 0. So your speedometer in your car gives what would be a rough estimate of the instantaneous speed of your car. The police officer who has the radar gun is getting an instantaneous speed, more or less, of your car. It's an average over a very short amount of time in any case. And if you wanted to get the average speed, you'd do something more like to take the idea of that cat again. If you want the average velocity, you time for 10 seconds and see what's the change in position of the cat's location. Maybe the cat starts at one wall and walks to the other, so you measure how far apart the walls are and you divide by the 10 seconds, and that's the average speed if the cat just walked it in a straight line. Even if the cat does not, it's the magnitude on average of the velocity, and then the direction might be an arrow pointing from one wall to the other. For speed, you do something very similar for average. You just add up how far total the cat has walked, how many steps, for example, did the cat take, and divide by that amount of time. And last but not least, there is acceleration. In physical science, we don't ever go beyond a constant acceleration, although you can have a change in acceleration as well. It's called jerk, actually. But acceleration is basically a change in velocity per unit time. And we can also talk about a change in speed per unit time, which is also called acceleration. So with these three terms, 4 if you want to throw in jerk, you can get quite a few motions that have been described. For example, if you take a rock or a ball and you throw it across a field, that motion can be described basically in terms of position and velocity and acceleration versus time. And the acceleration is more or less constant for that motion between when you've released the ball and when it hits the ground. To a very good approximation, it's a constant acceleration, provided that there's not like a very large wind that picks up all of a sudden. If you want to talk about the motion of a planet moving around the sun, that can be described using a constant acceleration. And in fact, if the orbit is circular, then it also has a constant speed. Not a constant velocity, the direction is constantly changing, but it has a constant acceleration and a constant speed. As it turns out, our planets move around more elliptical orbits, so the speed is also changing. So that is my brief intro to this topic, and I hope you enjoyed this video, and I hope that you found it helpful. And certainly I would like you to read through the lecture notes if you are taking this course from me. And thanks for watching.